So we have one more term to collect from the catalog. That would be our torsional stiffness in our joint. Now, expansion joints are extremely sensitive to axial rotation. Therefore, either you specify the proper stiffness or you check the total rotation on the joint, the total torsion on the joint, and make sure you're less than the value. The stiffness value in the Senior Flexonics Pathway catalog is not in the same table. They have a separate table for torsional spring rates. One note, if you're using this catalog, this is the wrong title on here. It's actually in 10 to the 6 inch pounds per degree. And Seizure 2 has the proper value in its catalog. Now, let's take a look at an example. We're going to use the expansion joint modeler in this example. And I wish to add an 8-inch, 50-pound class, 20 convolution joint to our existing model using the Seizure 2 expansion joint modeler. Now, what you will do first is select the modeler from the toolbar. If you're familiar with the toolbars, there's a group of red toolbars. By default, they're down the left sash of the program input screen. And the first are the hangers, and then there's our expansion joint modeler. Click on that button, or you click on the toolbar under Model Expansion Joint. Also, Control-J would do the same thing. But pick the icon or pick from the menu, and it'll open up the expansion joint modeler, and you focus your highlight on the element where you wish to put the expansion joint. Now, we are dropping in an expansion joint on an existing model. You might be putting an expansion joint in for the first time. So you're creating a new element and then calling out the expansion joint for that element. When you click on the expansion joint modeler, you will see this menu for Senior Flexonics Pathway. Other manufacturers who have given us data may not have the same layout, but it's a similar process. You will then just select the items from the list here. Pressure class, the style, there's untied, tied, hinged, gimbaled, untied universal, and tied universal joints. Those are the groups we have here. Then convolution material. This would be a function of what type of service, the corrosion considerations, erosion considerations. So here I'm going to leave it at 304 stainless steel. Convolutions. In fact, there are more convolutions listed here than in the catalog, but you can buy pretty much anything you wish, even odd numbers. But here's the ones that we are issued. I want to pick 20 convolutions. On the end type, we have both the from end and the to end of that element. I'm putting on slip-on flanges on either end. Usually slip-ons would be used for pipe under 24 inches. Above 24 inches, it might be plate flanges. Now on the bottom part of the screen, we have 3 columns. The temperature of the joint, the liner inside the joint, and the cover outside the joint. The liner and cover do not change anything other than add dead weight to the overall joint. Temperature is an interesting term. There's only one temperature here. This is the test temperature of the expansion joint. In the Senior Flexonics Pathway catalog, the stiffnesses that they list in the catalog are the stiffnesses at the test temperature. Now, this is 800 degrees Fahrenheit. If I run my system at 800 degrees Fahrenheit, then I have the proper stiffnesses. If, however, I have a system at a lower temperature than 800 degrees Fahrenheit, this processor here will allow me to modify the stiffnesses based on that change in Young's modulus. So you can get a stiffer joint if it's lower than 800, even more flexible joint if it's above 800. So that could be a useful term in some of these expansion joints. When you push the button, you say OK, what the program does next is then show you this screen here saying, OK, we were going from 20 to 30, that was one element, and now we have all these elements in this whole list. We have our slip-on flange, the expansion joint, then the slip-on flange on the other end, and then the remaining pipe. So it's still going from 20 to 30. But now we have another element, 20 to 24. Where's 24? That's the tie rod model, going right up the middle of the pipe. We'll take a look at that a little bit later. And then we're going to relate 24 back to node 23 to define the tie rod action. The bottom of the screen lists the stiffnesses, axial, lateral, angular, and torsional stiffness of the joint, this joint right here. And it lists the as tested stiffness, which match what's in the catalog, but it also lists this adjusted stiffness. If we click yes, we wish to adjust for temperature, we can then use these stiffnesses, and you see it's a little bit stiffer. One other item that is listed here is the allowed motion of the joint. This is overall length, and this is the same data that we saw in the catalog. In fact, there's another piece of data here, the torsional allowed movement. So if you click build, it will drop this expansion joint assembly into the model. And here's what happens. Here's that node 20 to node 30 up here at the top. There's 20 to 21 is the slip-on flange. 21 to 22 is the expansion joint. It's 12 inches and a half. Here are the stiffnesses from the catalog. 415 axial, 355 transverse, bending is left blank, effective idea specified, and also the torsional stiffness. So that's what the catalog will give you then, or the expansion joint modeler will give you. Let's take a closer look at that tie rod model that I mentioned earlier. Here's the element from 20 to 24. 20 to 24. 24 is the same location and space as 23. That's the end of the flange before we get back to a regular pipe. This is a rigid element. It shows a very skinny rod up through the middle of the model. What makes it different is that we then put this node C-node pair between 23 and 24. This will keep the two plates equidistant from one another, and it will not allow the rotation between the two flanges about the X or Z axis. So this is the key to setting the tie rod model in the expansion joint modeler. Again, in our input, we also have the effective inside diameter, so the program will automatically drop in the axial load up and down, and that load is equal to the pressure times the effective area of the joint. Since we have the tie rod model working in the Y direction, that load will be just putting the system in tension, and there will be no deflection of the system because you're just pulling on the tie rods. Now, when you put that expansion joint in the model that we've been working with down here, right on top of the top discharge nozzle, we can see that it moves around a little bit. And that's why we have the expansion joint in here. We want to see it move in the negative Z direction and in the positive X direction, and dropping those large bending moments on our pump nozzle down here, allowing this thermal growth to work by pulling the expansion joint around. So when you didn't have the expansion joint in there, it couldn't move around. Now it can, and this is going to be more relaxed system, much lower loads on our nozzle. So if you run this through Caesar 2, we see that the bending moments drop. This used to be 3.3 over here, and the limit was, if you do a complete check, 2. So now we're below 2, and perhaps we can save this system without any additional work. Now the question might be, where did I get these large Z moments? Didn't have them before. Those were rather low compared to where they were earlier, and it's mainly from the tie rod model. Again, perhaps universal tied joint would be a better application in this situation. Now, another thing we have to do with this joint is evaluate it. Is this the proper joint for the application? And we'll take this point up in our next session.